Hey people, let's start learning for earning.
A modern CNC spindle rotates at over 10,000 revolutions per minute, while an automated robotic arm can whip its tool center point across a factory floor at 5 meters per second. When these two kinetic forces intersect at the wrong time, the result is catastrophic. This destruction happens because the CNC machine and the robot operate as two completely isolated brains. They do not naturally speak the same language, nor do they share an inherent awareness of the physical space between them. The CNC strictly executes sequential G-code, reading hard-coded lines of coordinates one by one until a part is finished. The robotic arm, however, is driven by continuous logic, constantly reacting to environmental variables and input signals in real time. To prevent these systems from tearing each other apart, control engineers have to build a digital handshake, a reliable communication bridge that translates the CNC's rigid sequential code into signals the robot's continuous logic can understand. Without perfect millisecond-level synchronization between these distinct processing architectures, heavy machinery is guaranteed to destroy itself. At the base level of industrial automation, machines don't communicate through cloud networks or complex data packets. They talk through the physical switching of 24-volt direct current power. The CNC programmer initiates this conversation by embedding custom M codes into the machining program. While standard G codes dictate the tool's motion, M codes are specifically designed to trigger external hardware events. When the cutting tool finishes its final pass, the program reaches a specific line, say M80. This code tells the system the machining cycle is complete and the robot is clear to approach. Executing that M80 code causes a physical change. It energizes a coil and closes a mechanical relay mounted deep inside the CNC's electrical cabinet. The moment that relay snaps shut, 24 volts of DC current flow through the contacts, traveling out of the CNC cabinet and down a copper wire routed across the factory floor. This current needs a receiver. That receiver is the Programmable Logic Controller, or PLC. Looking at this architecture diagram, the voltage travels from the field devices and arrives at the input module, which serves as the gateway to the CPU. The input module detects this specific incoming 24-volt pulse sent from the CNC. It acts as an opto-isolator, safely recognizing the presence of voltage without letting raw power cross over and fry the sensitive electronics inside. Once verified, the PLC CPU translates that physical electrical current into a digital Boolean state. The 24 volts simply become a true, or a 1, in the controller's memory. The CPU processes this state through its scan cycle, a continuous loop that reads all inputs, evaluates the program logic, and updates the outputs, completing the entire process every few milliseconds. With the CNC's signal now registered as a true state in the memory table, the PLC can use it to trigger its internal programming sequence. The first half of the digital handshake is complete. A sequential software command inside the CNC was converted into physical voltage, carried across a room, and translated back into a continuous software state inside the PLC. To dictate exactly how the system reacts to that new software state, engineers use ladder logic, a visual programming language modeled after traditional electrical relay diagrams. The CNC's M code often only sends a momentary pulse of voltage. If the PLC misses it, the automation stalls. To fix this, the programmer writes a latching circuit, visible here on the top rung, to capture the request in memory. When the start pulse arrives, it activates an internal relay. The logic then routes that relay's output back around to run parallel to the start condition. Even when the CNC drops the physical voltage, this parallel branch keeps the system enabled. The request is officially latched. A latched request does not mean immediate action. Before any physical movement occurs, the PLC evaluates interlocks, the primary safety barriers in automation programming. A robust PLC program never blindly trusts another controller. It acts as a skeptical gatekeeper, independently verifying the physical state of the environment before allowing a robot to move. First, it checks the spindle. The PLC monitors an output directly from the CNC, confirming the heavy milling tool has completely stopped. Next, it verifies the physical safety door. A proximity sensor mounted on the CNC frame must report a true state, proving the door has retracted wide enough for the robot's payload. Finally, it checks the coolant system. The high-pressure pump must be off, so the robot gripper isn't blasted with industrial cutting fluid. As we see in this logic flow, these interlock contacts are placed in series. They act as logical AND gates. The signal from the latched request cannot pass through the rung unless every single one of these conditions is simultaneously true. Only when all interlocks clear does the logic flow reach the end of the rung. This triggers an output coil, which commands the PLC's output module to generate its own physical 24-volt signal. This new 24-volt signal is sent directly to the robotic arm. It is the definitive permission slip granting the robot access to enter the machine envelope and retrieve the part. Once the part is extracted, the entire process has to be reset. If the latch stays engaged, the logic will misfire on the next cycle. As the robot arm clears the door, it sends its own completion signal back to the PLC. This activates a normally closed contact in the ladder logic, breaking the parallel circuit and unlatching the system. With the robot safely out of the way, the PLC sends one final output back to the CNC, signaling it to close the door and resume its sequential G-code. The entire architecture works because the PLC operates defensively. By demanding independent verification of every physical state, it prevents the rigid sequence of the CNC and the continuous motion of the robot from colliding. This defensive design is mandatory because the factory floor is a hostile environment. It is electrically noisy, drenched in coolants, and prone to physical hardware degradation. One common hazard is the phantom signal, a vibrating wire or a sudden electromagnetic spike from a nearby motor, or a loose metal shaving can create a brief pulse of voltage that perfectly mimics a legitimate CNC command. A standard input rung operating at millisecond speeds would read that momentary spike, latch the circuit, and try to execute a process when no actual command was sent. To filter this out, engineers deploy a debounce timer, technically known as a timer on delay, or TON. As this signal map shows, the function block sits between the raw input and the latching logic. When the voltage arrives, the timer begins counting. If the signal drops before reaching a set threshold, like 500 milliseconds, the timer resets and the PLC ignores the event. Only a sustained, intentional 24-volt signal can bridge the gap. Then there are physical failures, like a proximity sensor on the CNC door that becomes blinded by a buildup of machine coolant and grease. Even though the door physically opens, the blinded sensor fails to send voltage. In the PLC's memory, that specific interlock contact remains false. The logic flow hits the false contact and stops immediately. The robot is denied permission to enter, and the automation sequence safely stalls before a crash can happen. When a maintenance technician plugs a laptop into the PLC, the live ladder logic highlights exactly where the signal is breaking down, instantly pointing them to the blinded sensor. Professional PLC programming anticipates failure. It is entirely defensive, designed to handle physical anomalies safely, rather than assuming perfect conditions on the floor. Despite the rigorous interlocks we've just looked at, there is a critical distinction in automation engineering. Standard PLC control logic is never used to handle human life safety events. A standard PLC is still a computer. Its microprocessors can freeze, its operating system can glitch, and its millisecond scan cycles introduce tiny, unacceptable delays in an emergency. For critical safeguards, like light curtains and emergency stops, engineers use deterministic safety circuits. These are hardwired pathways designed with absolute, guaranteed response times. Hitting the e-stop button doesn't politely ask the PLC software to halt the program. It physically bypasses the standard logic controllers altogether. The safety circuit routes directly to heavy-duty mechanical contactors. Pushing the button violently severs the high-voltage three-phase power flowing to the servo motors, killing the system's kinetic energy at the source. This strict hierarchy is the golden rule of systems integration. Standard control logic ensures a machine never moves without explicit, verified permission from adjoining systems, and life safety systems never rely on standard software to stop a threat. The 24-volt physical handshake we've outlined is incredibly reliable for binary commands like start, stop, and door open, but it hits a hard limit when you need to share complex data, like precise coordinate streams or live motor torque values. You can't run 1,000 physical wires for 1,000 data points. To handle massive data flow at sub-millisecond speeds, the factory floor leaves the hardwired relays behind. The architecture shifts into industrial Ethernet and high-speed field bus protocols like EtherCAT, which is exactly how modern production lines coordinate thousands of axes at once. We'll cover that in the next episode.
Thanks for watching. Please visit the channel for such more content, and don't forget to subscribe the channel and like if it is helpful to your knowledge, and comment if something is wrong.